Okay, good morning, everybody. I'm going to show you a video today that has just been a thorn in my side all week, and I've watched it a bunch of times trying to make sure I had my notes and that I've seen everything, didn't miss something. But Kent Hovind is a man that continuously purports himself to be a man of science. Listen to any one of his videos or debates, or he tries to debate scientists, and he'll tell you, I taught science in high school for 15 years. And if you say anything to him, he'll say, I taught geology in high school, and I taught algebra in high school. And so he thinks he knows all this stuff. I'm here to tell you that he doesn't present that he knows all this stuff. He absolutely shows no clue whatsoever as to what science is, how it works, or any, especially any of the scientific fields like biology or evolution or geology. And this is another one of those. So let's just look at this video.
Areas all around the world, you have rock layers thousands of feet thick, bent and folded without fracturing. They've been bent and folded without fracturing. But how can that happen if they were laid down separately?
By the way, Matt, do you know who this guy is talking?
I don't, but he's making a great point.
I've never heard him before, but I like him. Give me a call. Have you on our program. Come on down. Please do. Go ahead. Okay.
For hundreds of millions of years and already hardened.
The thing is, these rocks don't fold over 5 minutes. These folds are caused due to considerable compressional stress over millions of years.
Oh, how do you know that, Dan? Did you watch him?
How do you know it's not, Kent? Did you watch them? Did you watch those folds being made?
Now, come on now, Dan. Sign, man, Dan. Anytime you say millions of years, you're taking it
Come on now, Kent the science gent.
away from observable science, aren't you?
Usually caused by the movement of the continental.
So he mentions observational science, because to him anything in the past has got to have been somehow observed. He thinks, the Rocky Mountains rising up, being folded and pushed up, is something that somebody should have stood there and watched. I don't know how. So it's okay for a creationist or a Bible thumper like Kent to say stuff like this, because he doesn't want to provide scientific proof for creation. He wants you to provide him proof that it's not creation. And so I'm getting a little off topic here. But the idea is that there's a lot more science to science than observation. You can also have analytics and go out there in the field and study those rocks and analytically figure out how those layers could have gotten there.
They smashing into each other at the speed of fingernail growth.
And do you know that too? Could there have been rapid movement for a few minutes and then slow down to the fingernail growth? You don't know any of that. This is not Simon, Dan. This is
Once again, he says Simon Dan doesn't know that, but it's okay that he wasn't there. You don't know that there was a rapid collision and then slow growth or slow movement. You don't know that. You just think that.
Try bending a slab of rock, a slab of concrete, any type of rock, try bending it, it's not going to work. But if the concrete is still wet, it can be easily folded without breaking.
So you can fold wet stuff now. Fascinating.
Dan, think about it. If you had a layer of wet clay, could you fold it and shape it into something? Yeah. If you had a layer of hard clay, could you fold it? No, it would snap. Dan, you're a Simon. Come on, put on your...
Okay, so here's another one of his big things is that rocks cannot bend. And believe me, I worked in geology labs. I know how it works. They take samples. They have put them through temperature and pressure, bending and breaking, and there are parameters. You can look up a parameter for any kind of rock that has to do with how much it will bend before it breaks or breaks before it bends. Those are all things that were analyzed in the laboratory. They're all science. What you're doing is you're pulling stuff off the top of your head and saying, I don't know how it could be done. I don't know how rocks could bend like that. So it's impossible. Right? Let's listen to some more.
Hat and think for a minute, okay?
Same principle applies to sedimentary rock layers. They can be bent and folded soon after the sediment is deposited.
The problem is, when that sediment is deposited, it's not rock, it's sediment. That means in order for it to fold like this,
They call it sedimentary rock.
you need a comparatively short amount of time. There is no evidence to suggest that this is how these layers form.
Dan, there is every evidence to suggest that. If you have 20 or 30 layers,
There is no evidence to show that 2,000 feet of layers of rock can all be deposited by one flood of water, if you want to call it that. It can't happen. In case you didn't notice, take your water hose outside and point the water at the ground. How much deposit does it make on the ground there? How much does that deposit? I can show videos of you and your little flood thing that you had, and there wasn't a single particle deposited in that break in your lake. So 2,000 feet of layers of rock do not deposit all by themselves. Not to mention that, talking about the Grand Canyon, each one of those layers has a life that evolved and went on while that was being deposited. You can analyze that. You can take a sample of it back to your lab and look at the chemistry, dissolve it, look what's in there, and see that it was doing something for a million years, while waiting for something else. And so each layer does that. It's not hard, Kent.
All of them bent, and none of them with fracture marks. I mean, if you think all the layers are different ages, well, the bottom layer would have hardened, and you'd bend it, and it's going to fracture. I showed this clearly. This guy's going to talk about it. I'll show you a video in a minute. All the layers were soft at the same time. All of them bent at the same time, while they were all still soft, indicating the layers are not vastly different ages, are they?
Once again, I'm sure that all the layers bent at the same time. They were bent by the same force. In order to get that much force, maybe it was the continental plates, but there's no reason why it couldn't bend without breaking.
The natural cements have a chance to bind together the particles into hard little rocks. Grand Canyon is a great example of this. The canyon walls are hundreds of feet thick, containing multiple rock layers. Yet, somehow, this whole sequence of rock layers was bent and folded without fracturing.
If you think that 50-foot wide river at the bottom of Grand Canyon made that mile-wide canyon, and in some places 18 miles wide, you are certifiably insane. That river?
Okay, Kent, once again, you're looking at the grandeur of that canyon and the way it was made, and you in your tiny little pea brain cannot see, oh, that big canyon could not possibly have been carved by that little tiny river way down there at the bottom. Well, you're wrong. That's how it works. It's moving water that carves the rock. It's not standing water. It's not flood water that carves through the rock. It's moving water. And it has to be moving a long time to cut down through all those layers down to the bottom.
River just flows through the crack left over in Grand Canyon, probably formed in about a week or less.
You really think it formed in a week? I think originally in your lectures you were saying it formed overnight.
We'll cover that on video number 6.
Well, as discussed, this is a very slow process. As with the Grand Canyon, this is only visible because the Colorado River cut its way through it.
Dan, let's focus. The top of Grand Canyon is about 8,000 feet above sea level, whatever that is in meters for the queen to keep her happy. The river enters the canyon at less than 2,800 feet. Rivers don't flow uphill. That river did not make that canyon. The river flows through the crack left over, that's all. Rivers don't flow uphill. The top is a mile high.
It's just a wonder how you can carry this crap around in your brain without leaving a stench where you go. The Grand Canyon is at about 7,000 feet elevation. The Colorado Plateau there. The Colorado River, its headwaters are up in Colorado in the Rocky Mountains, above 9,000 feet. And that water flows down where it comes into the Grand Canyon, and then it drops 2,000 or 3,000 feet. It drops down another 3,000 feet. So the river is high enough, and the river started its carving of the Grand Canyon when it was very small. If you do woodworking, or you had somebody carving one of those, bear out of a log, you can see that it takes time to carve that and make those carvings. And if that was to happen all at once, in one night or in 1 week, there's not time for it to make all those beautiful patterns and the buttes and the mountains and carving the rock there. It just doesn't work that way. It's the river and its meandering that carves all those beautiful inlets and things. If the floodwaters went through there and made one pass, it's just going to make one cut. And you can obviously see, if you look at even the picture he had, you can obviously see it was more than one cut.
Than where the river starts entering the canyon. Do the math.
Given time. Again, something which would have taken millions and millions of years.
But that's impossible if the first layer, the peak sandstone, was deposited over North America 460 million years before being folded. But if it all happened during a recent global flood, those layers would still be relatively soft and pliable.
But how does a global flood lay down up to 20 layers of sediment all at once?
Glad you asked, Dan. I want to show you. This has been done years ago. There's a video called Experiment.
Okay, before we go on into this, I just want to say you've got two things going on here that are being conflated. And I think you don't even realize what you're saying. First, the layers have to be laid down. There had to have been a large flat plain out there. And then what the Colorado River began its carving of the canyon. So the water didn't somehow, I'm not even sure how, if you understand how water, are you saying that it came in and deposited all that, and when it's going out, it took out the canyon? You've got a lot of things that you don't understand there. So anyway, he's about to switch to a video from the Colorado Engineering Lab, where they have set up to do river sedimentation. What they're looking for is the sedimentation along the banks of a river or at the inlet where a river goes into a lake or ocean. And so that's what they're studying here. Let me get to the start of that. So here we have, he's going to show this video by Dr. Pierre Julien, who is a very renowned river hydrologist. He studies sedimentation in rivers and river deposits. So let's listen to him for just a minute.
and small particles in between. When we set this mixture into motion, the small particles which have a lower kinetic energy fall between the coarse particles and deposit on the bottom of the moving layer. The coarse particles with higher kinetic energy roll on top of the fine bed of fine particles. Particle segregation occurs under lateral motion in the mixture. Coarse black particles roll on top of fine particles when
But I know we're getting into something else here, but let me tell you that the small particles don't have different acceleration, velocities, movement than the bigger particles. Okay? In fact, if you look at river deposits, you can go anywhere, look at a creek or look at a river. You can study glacial movements, and what you find is as the river slows, as it slows, bigger particles, rocks and so forth, fall out and are deposited because it takes more energy to move them along. So those bigger particles fall out. The smaller particles, the clay and sand, are carried in water until it slows down almost to being still. And then those are deposited. So I wanted to tell you that before we get into this.
Oh, why was one to the bottom? Let's keep watching it.
particles under high load shear stress also display the same particles
Now keep it in mind. Oh,
The fundamental
keep in mind, during the flood of Noah, the earth is continuously turning under the moon. The moon's gravity pulls up a bump called the high tide and holds it like a magnet. As we turn around, that bump stays under the moon because of the moon's gravity. But on Earth, people are seeing the water go up, down, every 6 hours, 12 and a half minutes. Well, if the water's going up and down, that means it's also coming in and out of the bump. You're getting lateral movement constantly during Noah's flood. So watch. Dan, pay attention. Focus.
Okay, once again, he's trying to make something simple, I guess. If the earth were covered with water and it's still rotating, yes, the moon has a pull on the earth. Its gravity pulls on the earth, and there would be a bulge. And that bulge is there all the time. It's there today. And it would go up and it would go down. Water comes in and comes out, whatever, But realize that that is a very slow movement. You need a lot of movement, a lot of kinetic energy to drill out that canyon or any canyon.
The question about lamination is the following. Does nature use repetitive segregation under a continuous supply of sediment? First, the submerged conditions are examined.
Pouring through the water.
Turbulent fluid motion surrounding the particles led scientists to believe that lamination was caused by periodic cycles of turbulence. When the same experiment is carried out in the air,
No water.
second income displays all the features of lamination through repetitive segregation. Moreover, the laminate thickness increases with the heating rate of the sediment mixture. It should be noted that laminated film in the direction of motion, here, at an angle exceeding 30 degrees.
Given the absolute vacuum is at minus 29.92 inches of mercury, the hypothesis of turbulence is tested near a complete vacuum at minus 22 inches of mercury. Levitation develops without the presence of a surrounding fluid. Lamination therefore depends on the mechanical interaction between particles of different sizes, different shapes, and different densities.
Okay, so I'm going to stop it right there. What he's doing is he's got 3 experiments running right here. He did some deposits through water. So he had some water in a little tank, and he poured the deposit in a single stream to see how that one stream of pebbles is going to lay down layers. In the one with the water, he didn't get any layers. In the one with the air, if those pebbles were being laid down, on the beach or something, he did get layers. And then the third one is in a vacuum, and you can see some layering, but it's different than with air pressure. And so what they're comparing is the angle of the deposit and how that might change as the rocks are deposited. But remember also that they're being deposited from one source, one down source. Okay?
Under submerged conditions, lamination also occurs during gradual aggregation of the bed under plain bed conditions. Here's the same lamination sequence in accelerated motion. Large-scale experiments on stratification carried out at the hydraulics laboratory of the Colorado State University Engineering Research Center. For the experiments, a 4-foot wide flume measuring 60 foot long recirculates 1,000 cubic feet of water and 8 tons of a sand mixture. This flume provides a continuous supply of coarse and fine sand particles under steady discharge conditions.
So you're seeing there the flume where the water comes through, and it's carrying the particles of the different particle sizes. And here's Dr. Julian again.
Consider a typical delta sketched on the board. At the initial time T1, the delta is comprised of 3 parts: the top set, the foreset, and the bottom set slope at initial time T1. Over time, the force particles rolling on the bed slide down the foreset slope of the delta and accumulate as the delta progresses in the downstream direction. Finer particles rolling on the bed settle.
So you notice he's saying the particles are going down the delta, where the slope of the delta, and that's how they're being deposited.
Form a layer of finally fine particles. The particles in suspension are carried through and deposited on the bottom set slope of the delta.
After a certain time interval, you get a second.
Okay, again, he's saying that the particles that are suspended in suspension go out further. They don't just roll down the delta sides, they go out further and are deposited out into the bed of the lake or whatever it is.
Rainfall cloud at time T2. The sediment accumulated on the bed from time T1 to T2, you find what is called a layer of sediment. The layer of sediment is the accumulation of sediment between the initial time T1 and the subsequent time T2.
So you notice him saying that there's time T1 where he marked that was already, everything was deposited. So that was at T1. Then time passed. Oh my goodness. Oh my goodness, Kent. Time passed. And there's T2. Those other sediments were deposited later than the deposits at T1. Imagine that. They're older. Or
Watch that.
Gradually progresses in the downstream direction. A close look at the top set slope in slow motion clearly shows a laminated deposit of fine particles. The thickness of the top set deposit decreases in the downstream direction as the first set slope of the delta is approached. Over a long period of time, the accumulation of sediment displays clear stratification, with fine particles on top, coarse particles in the middle, and fine particles on the bottom. It is important to understand that the chronology of the formation of the deposit depends on the layers and not on the strata.
Now watch that. Here's where
Zones correspond to the interface between successive layers, not strata. The thickness of the strata is determined by the changes in sediment transport that occur in non-uniform flow.
non-uniform flow. If it's flowing faster, you get more. If it's flowing slower, you get less. This is what happened during the tidal changes in Noah's flood. Think about it now. It's deposited horizontally, not vertically. You guys keep playing the top layers younger. Keep watching. Pay attention.
This is now considered two particles in the delta. Particle A in the upper strata, and particle B in the lower strata. Particle A deposited at a time T1 before particle B. Particle B in the lower strata, therefore deposited after particle A in the upper strata.
Did you hear that, Kent? Particle A deposited before particle B. It was deposited, and then B was deposited on top.
Increasing the flow depth while keeping the discharge of the supply of sediment unchanged results in more complex sedimentary features. Substantial deposits accumulate with features including deltas, dunes, and ripples at various stages of development. A granite delta, viewed from the plume sidewalls, displays clear stratification characteristics in terms of the superposition of deposits with similar particle size distribution. A cross-section is cut through the delta to examine the primary features of the processes of sediment mixtures carried out under steady flow and the continuous sediment supply. The cross-section displays a clear superposition of strata of fine particles of white and
Okay, I want you to notice here, Kent, that the water came down the flume and made its deposits. He took his cross cut 90 degrees from the movement of the water. So he's looking across the movement of the water. He's seeing this deposits as the water slows down at the delta and deposits its sediment.
first particles in black with clear lamination. Looking at the cross-section of superposed strata, it is tempting to conclude that the strata correspond to successive sedimentary layers, but they result from discontinuous sedimentary periods, that each strata is younger than the one underneath it, and older than the one above it.
So what was that he just said? Each strata is younger than the one underneath it and older than the one above it. What a statement to make, Kent. Each sediment layer, he says, is younger than the one below it and older than the one above it. Imagine that, Kent.
And at all points of the same strata have the same age.
The stratification experiment invalidates these hypotheses because these strata are not identical to successive layers. Moreover, clear stratification is observed when there is continuous supply of a certain sand particles.
Why is this important? Well, quite simple.
Okay, they go through some stuff here, and let me see if I can find the... So here he is, he's talking about fossils now. There are fossils at the bottom, there are fossils in the middle, and there are fossils or creatures near the top. They're not fossils yet. And he's saying that they're buried by the sediment that comes in from the river over the side of the delta and covers them up. Watch.
Ecological levels. A heavy influx of sediment arrives and they all get buried. Eventually, if no air gets to them, they could turn into fossils. Obviously, those buried in the top strata are the same age as those in the bottom strata, as they were buried in the same layer of sediment. Then another heavy layer of sediment arrives.
Okay, Kent is going to obviously say that the fossils at the bottom are younger than the ones in the middle, and that's not true. Once again, you have completely missed the whole reason for the video. If you think that a fish is going to swim around and lay there, in water, waiting for sediment to cover it up, it's not. And so, sure, sediment comes in from the river, flows down the delta, and deposits. But chances are there's not going to be any fossils in that sediment because those creatures are going to move out of the way, or they're going to be washed out of the way by the water. Fossils are generally buried by sediment that comes down and lays down flat.
And more sea creatures are trapped. But what is more important is the ones at the top of the previous layer were buried before the one in the bottom of the last layer.
Okay.
So the one at the top here is older than the one at the bottom.
Wow.
Director of the research program explained.
Okay, that is not true because that's not the way fossils are buried. Geologists know those things. They know, like you saw, they know how the river water is going to come in, rush in, and deposit its sediments at the delta. But that is not the way that fossils are going to be buried. Those sediments that are coming in are still soft, and the water carrying the sediments is going to wash away whatever sitting there before it ever deposits anything. So, unlike any of the other stuff in that video, that part is wrong, just flat out wrong. And so this is another video that Kent has graciously supplied us with, and I can guarantee you that practically every thing out of his mouth is wrong. So, if you guys want to, if you want to be learning geology, learn about how fossils are deposited and created, I would encourage you to take some classes, and especially Kent.